So we've been studying square roots and cube roots, right? And we've been using the radical notation. Radical notation. That is this right here. Okay, that is the square root, and this is the cube root. The square root has an implied number right there. What is the implied number for a square root? A 2. Okay, so if you see a radical like that, that's what that's called, a radical, and you don't see a number there, everyone knows that we're talking about a 2. But if you see a different number there, or you want it to be a different root, you have to put that number there. It's required. So this is the cube root, which means uncubing something. This is the square root, which means unsquaring something. It's super important when you go on to the next level, especially whether you're doing free cal or even calculus, especially that we can get rid of those radicals so that we can manipulate the expression or the number more easily. And in order to get rid of the radicals, we write those equivalently in what's called rational exponent form. Right here, rational exponent. That's what I'm looking for. Okay, so a radical expression can be written as a rational exponent. A rational number just means a fraction. Okay, it's going to be a fraction. So here's what's cool. Every single radical can be written equivalently as a fractional exponent. I'm going to show you what it looks like right here, off to the side in the top right. The square root of x is the same as x to some power, okay? And it's actually to the 1/2 power. The square root of x is the same as x to the 1/2 power. Where does the 2 come from, you ask? The 2, oops, that's too big. The 2 that we have right here in the denominator of my exponent is the same number that is implied right there. It's a 2. We call this number the index, okay, or the root index. It's the index or the root index. So here's an easy way to remember. We know that the exponent is going to be a fraction, and we know that a fraction has a numerator and denominator. Where did the 2 come from? It came from the root. So think of the horizontal division bar as being the ground. Where do roots usually grow? Above ground or below ground? Usually. Below ground, yeah. So the root index of 2 goes underground in the fraction. It's the bottom piece, okay? So where does the 1 come from? Well, the 1 is essentially this number here. It's x to the first power. Okay, so what we did is we left the exponent that's already there, implied 1, and we took the implied root of 2 and put it underground, where the roots normally live. Okay, based upon that explanation, what do you think the cube root of x can be written as with a fractional or rational exponent? X to the 1/3 power. And guess what? You would be absolutely correct. Okay, now once you see how the trick is done, if you will, we can actually go to higher order roots. That's the 4th root of x. Guess what that's going to be? That's going to be x to the 1/4. Yeah, again, to reiterate, the root index, or the root itself, ends up being in the denominator of your fraction, underground. Let's do one more, just to make sure you got this. The 5th root of x would be x to the what power? 1/5, so on and so forth. That continues forever. You can take the 6th root, you can take the 100th root of a number. The 100th root of a number is just asking yourself what number times itself 100 times gives you that number. It's not that easy to work with, but we could do it. Okay, now let's look at something else here. What if I have the square root of x cubed? What if the number underneath there, or the variable underneath there, already has an exponent that's not a 1? Can we accommodate it? What did you say? X to the 3/2. There you go. The 3 stays in place, really. If you could think of this 3 as being like 3/1, can't you? Oops, that's not a good color. It's like 3/1. So the 3 is already in the numerator, if you will. What becomes then is the denominator becomes the root. Let's try another one. What if I have the cube root of x squared? What would that become? X to the 2/3 power. Yes, yes? The 2 stays in place. It's already in the numerator on the exponent, but the root 3 goes underground. There you go. How about this one? How about the 15th root of x to the 27th power? That's right. That's right. Now, there's a couple of reasons why we want to have another way to express these numbers. If I ask you what 4 to the 1/2 power is, 4 to the 1/2 power, because it works from left to right, it also works from right to left. If I ask you what 4 to the 1/2 power is, you probably don't know what that means until you convert it back to this, right? But if I ask you what the square root of 4 is, you all say what? 2, because you think better when you're evaluating in terms of radical. What if I say, what is 9 to the 1/2 power? What's 9 to the 1/2 power? 3, because that's the same as the square root of 9, which is 3. But if I ask you 9 to the 1/2 power, it's like learning a different language. You're not thinking in that language yet. You're converting it back to the original language. If I say 9 to the 1/2 power, you convert it to the square root of 9 first, and then you're like, oh, that's 3. Okay. But the reason we want to be able to express them as rational numbers or rational exponents is because we can use the rules of exponents, PEMDAS rules. We can use the rules of exponents on the rational number where it's harder to manipulate this if it stays in radical form. For instance, if I ask you to simplify the 15th root of x to the 27th power, you might not even know where to begin, would you? How do you simplify the 5th root of x to the 27th power? You got me. But if we write that as a fractional exponent, x to the 27 divided by 15th power, now asking you to simplify that is really the same question as, does 27/15 simplify to anything? It does. It has the 27 and the 15 have a common factor of what? 3. So I can divide the 3 out of both of them, right? 27/15. If I divide the 3 out, it gives us 9/5. And now let's do this. Let's convert x to the 9/5 back to radical form. It's going to be the what root of x? The 5th root or the 9th root? The 5th root, right? It's easy to remember. The underground part, the bottom of the fraction, is what we call the root. And then it's going to be x to the what? Underneath the radical? 9. Yeah. So did y'all realize before today that the 15th root of x to the 27th is going to give you the exact same number as the 5th root of x to the 9th? Did you know that? Probably not. Do you know that now? Yeah. Do you want to memorize that fact? No. But do you want to memorize how we got from there to there? Yeah, that's the method. That's the algorithm. That's what you want to know. Okay. So in general, here's what we could say. In general, the nth root of x to the mth power, the nth root of x to the mth power is the same as x to what power? M over n. Yeah. There you go. And vice versa, right? X to the m divided by nth power is also the nth root of x to the m. It works both ways. It works both ways. So let me give you this example. What if I ask you for 8 to the 2/3 power? And I ask you to simplify that. Yes, 8 is acting like the x. It's the base. Is it square root or cube root? What's in the bottom? The 3 is in the bottom, so that's underground. So it has to be the cube root of what? 8 squared. So that's rewriting it in radical form. Remember I said when you learn a new language, you have to convert it back. Is that something that we can work with now? What's 8 squared? Whoa, there's a bag there. No, it's my fault. That's 64. So that's the cube root of 64. And now I can ask myself, self, what number times itself 4 times is 64? 3 times. Is it 1? 1 times 1 times 1 is 1. That's too small. Is it 2? 2 times 2 is 4. 4 times 2 is 8. That's too small. Is it 3? 3 times 3 is 9. 9 times 3 is 27. That's too small. Is it 4? 4 times 4 is 16. 16 times 4 is 64. It is 4. So 8 to the 2/3 power is also known as what? 4. It's the exact same thing. How did I get there? Well, I wrote x to the 2/3 as the cube root of 8 squared. Are you okay with that? That's the new part of the, and then I just evaluated 8 squared. That's 64. Now, when I ask you for the cube root of 64 without a calculator, which I will, you're just asking yourself what number times itself 3 times is 64. And I just went through the integers, 1, 2, 3, and 4 words. What is 5 cubed? 5 times 5 is 25. 25 times 5 is 125. That's too big. So it's 4. Now, watch this. This is the strategy that you want to use the rest of your life. I preach it in pre-cal. I preach it in calculus, and people are like, what? You never told us that. I did. If you're doing something without a calculator, it's better to do it in an order that makes it easier. For instance, here's what I want to tell you. The cube root of 8 squared, those are both exponents. So when you talk about the PEMDAS, these are both at the exponent level. When you take the cube root or you square something or whatever, it's all at the E level because we now know a radical is just an exponent in disguise, don't we? A radical is an exponent. You could do those in any order. You could do them in any order. So the cube root of 8 squared is really the same thing as the cube root of 8 squared. Now, what's the difference? The difference is the order in which you do them. On the left, you're squaring it first, which makes the number bigger, and then you're cube rooting the big number. But it works the other way around as well. In this one, you're taking the cube root of 8 first and then squaring it. You're just doing it in the reverse order. It doesn't matter the order. It's like multiplication and division. As long as you do it from left to right, it doesn't matter. What's easier to do? Well, let's try this version. This has parentheses. So if we take the cube root of 8 first, what's the cube root of 8? 2. What number times itself 3 times is 8? 2. So that becomes 2 squared. What's 2 squared? 4. Holy moly smokers. Which version was easier, going big then small or small then big? There's the strategy. That's the revelation. You never told us that. Go small, then big. And that's just in life. When you're doing PEMDAS, look to subtract before you add. Look to divide before you multiply. Look to take a cube root before you square. Make the number smaller and then make them bigger, rather than make them uncomfortably big just to have to try to make that number smaller again. All right, so when it comes to evaluating, is it big then small or small then big? Small then big. Small then big. Okay, good. Whew, let's try this one. Let's try, how about, let me give you another one. Let's give you another example. How about the cube root of 64 squared? Let's try that one. Yeah, that's what we just said, right? Unless you want to go the other way. What's 64 squared without a calculator? 64 squared is big. And now I have this big number, and I got to take the cube root of that big number? Whoa. No, thank you. But can we take the cube root first and then square it? It works. It would work. Let's try that. What's the cube root of 64? 4. We just learned that. 4. What's 4 squared? 16. Guess what the answer is? 16. We get the correct answer before someone who goes 64 squared first is like, I just peed in my pants, sir. I can't do that. We got the answer. Go small before you go big. This is the cube root of 64 squared. Just because I wrote it with the squared first doesn't mean you have to square it first. This is 4 squared, which is 16. You got it? Yeah. Boy, it's fun easy, isn't it? Okay, so just some terms. Again, the thing that's written in the crotch, the index is written in the crotch. If you don't see, or the V, if you don't want to call it a crotch, you can call it a V, whatever. I call it the crotch. That's what it is. It's a crotch. If you don't see anything, it's implied to be a 2. It's never a 1 because we don't need it for a 1. but any other number, it's going to be n. It has to be defined. And then the thing under the radical is the radicand. This is the thing under the radical. Okay, and of course the radical is the symbol. All right, let's jump down here. We've already done this one. Let's try this one. 27 to the 2/3. Let's jump down here. 27 to the 2/3. If we want to simplify that one. Now let's see if we can do this without converting it back to a radical. Okay, because that's really the thing I want you to try and learn. Try to learn and think now in the new language. This is one of two things. It's either 27 squared, then the cube root, right? Or it's the cube root of 27, then squared. If I square it first, that's making it bigger. Ugh, yucky, yucky, gross, gross. And then making it smaller. But if I get the cube root first, that's making it smaller just to make it bigger. What's the cube root of 27? 3. What's 3 squared? 9. Guess what the answer is? 9. Yeah. The answer is 9. See? We grouped it that way. It's 9. All right. What about 4 to the 3/2? It's a fractional exponent. So this is either 4 cubed and then the square root, or the square root and then cubed. Let's go small first. What's the square root of 4? 2. What's 2 cubed? 8. The answer is 8. Is that how they did it in your example? No, they did it the other way. They went 4 cubed first, which is 64. And then it asked for the square root of 64, which is 8. Now, sometimes when you go big, before you go small, the number is big, but it's still manageably so. Like 64 is still a big number, but we know what the square root of 64 is. But as a general strategy, go small before you go big. Okay? I would write this as the square root of 4 cubed. Más mejor que bueno. Más mejor que bueno. More better than good. Okay? Go small before you go big. All right, so this is doing it the other way. All right, so here we go. We got to summarize now. You have the nth root of x to the m. The index is called m. The thing under the radical, which is x to the m, is called your radicand. And we know that these two are equivalent to each other. Instead of an equal sign, this is a double-headed arrow. You know what an arrow means instead of an equal sign? Yeah, I put an equal sign in between there. I like the equal sign better, but this arrow mean implies. That's what an arrow means. If you ever see an arrow, it means implies. So the left side, because the arrow goes from left to right, the left side implies the right side, which means if you have the left side, then you have the right side. But the arrow works the other way around too. So if you have the right side, it implies that you also have the left side. So in this case, an equal sign is really the same as the double-headed arrow. If you have one, you have the other. Okay. Now it's also worth adding to this. This can be written two ways. It could be the nth root of x to the m, or it could be the nth root of x to the mth power. Either one of them. Which way is easier to write if you just want to present the final answer? Which one has fewer symbols? The left one, right? For presentation. This one is for presentation. Okay? This one is for using. You got it? If I actually want to evaluate something, I'm doing the one on the right. I'm going to make it small before I make it big. But if I'm writing a final answer and I don't want to have an extra set of parentheses there, this works fine. Okay? It means the same thing. Everyone knows that. That's why we don't have to have the parentheses. So for presentation, for using. Got it? Okay. Okay. Let's go ahead and go through and do some of these 12.1. We'll simplify. All right. Answering the questions. Number one. What is the index for the radical expression? 4. All right. Cool. That's all that one was. That's the 4th root of x cubed. Cool. What is the radicand for the expression the cube root of x to the second? Or 6 to the second, sorry. No, 2 is the exponent of the radicand. What? 6 squared. Yes. The radicand is everything under the radical. Yeah. The radicand is everything under the radical. Got it? Okay. Write the expression in radical form. Okay. We got this. X to the 2/7 can be written as what? Let's do the presentation style first. What would be the presentation style? Is it the square root of x to the 7th, or is it the 7th root of x squared? Okay, I'm going to do both and draw an x through there. You know how many people in calculus, when I say x to the 2/7, say, the square root of x to the 7th, sir? And I'm like, go back to algebra 2. And like, which way is that? And I say, out the window. Okay, okay. Yeah, you're not going to get that confused, right? Now, what would be the other way if we wanted to use it? I wouldn't put the squared under the radical because that implies to do it first. I would put the 7th root of x and then the whole thing in parentheses squared. Yeah, they mean the same thing. One's for presentation, one is for usage. Present, use. Got it? They mean the same thing. All right, letter B. Holy crap. Holy crap. Oh, don't let this bother us. Let's do the same thing. Here's we'll do the present on the left, and we'll do the use on the right. What is the presentation? It's going to be x squared, and then it's going to be the what root? The third root of that whole thing to the what power? To the 4th power. See that? Yeah, I'm just saying this blob is that blob. That blob is that blob. Now, does that simplify? What do we know about the thing under the radical? When we raise a power to a power, what do? We multiply, right? So what does 2 times 4 become? 8. So that really becomes what? Let's put it back in fractional exponent now. That's really x to the what power? 8 divided by 3rd power. Hey, wait a second. That's x. If we're raising a power to a power, and all we have to do is multiply to get the new exponent, couldn't I have done that in the beginning? Am I not raising a power to a power right there? So off to the side of my workbench, what is 2 times 4/3? Well, that's 8 over 1 multiplied. That's 8/3. Hey, there's the other reason why we want to be able to write radicals as fractional exponents. It allows us to use the rule of exponents, like we've already learned, more easily, and we can get down to final answers more quickly instead of having to go through the radical format. The rules of exponents still apply. Okay? Now let's write that back in radical format. What would be the simplified radical format? X to the 8/3 becomes what? The 8th root or the cube root? The cube root of x to the 8th. There you go. There you go. Now, of course, if we want to use this, we're going to say it's the cube root of x to the 8th power. Okay? When you're raising a power to a power, you just multiply. But anytime you're going from one to the other, the index is the root. We can call it the root index. Instead of calling it the index, just call it the root index or just the root. The roots are found underground. Underground is in the denominator of your exponent. Got it? Okay. Got it. Good. How about this? Write the expression using a rational exponent. The 4th root of x to the 7th is what? X to the 7/4. Yeah. Now watch. Here's another reason to convince you that the order doesn't matter. This is the same thing as the 4th root of x to the 7th power, right? It's the same thing. The one on the left is how we present it because it doesn't have the extra parentheses. The one on the right is how we'd use it. Watch this. Let's split this up. Let's say that x to the 7/4 is x to the 1/4 to the 7th power. Or if we do it the other way, it's x to the 7th to the 1/4 power. Would you agree with me? The reason it works, again, is because the rules of exponents. In both cases, I'm raising to a power to a power, aren't I? So in both cases, what am I going to do with those two numbers? Multiply them. Isn't multiplication commutative? 2 times 3 is 3 times 2? Yeah. A fourth times 7 is the same as the 7 times the fourth. It works either way. But if you analyze it in the order of operations, the one on the left takes the fourth root first and then raises it to the 7th power. That's small then big. Whereas the one on the right raises it to the 7th power first, makes it bigger, and then goes smaller. It doesn't really matter which way you do it. Go big then small or small then big. It doesn't matter. But if we don't have a calculator, David, it's probably better if we do what? Small then big or big then small? You help David out. Small then big. No, that's fine. That's okay. Small then big. Sometimes we can all use a little help on a Monday. Small then big. If we don't have a calculator and we're trying to evaluate it, go small before you go big. It makes the numbers manageable. Okay. Holy crackerjack. This is the what the heck? Okay. All right. It says to write it using a rational exponent. Okay. Step 1, I have something to the 3rd power. I'm not going to focus on that yet. I'm going to focus on that. That is a quantity. The radicand is 5x. And because it's the square root, it's going to be to what power? What number is implied right there in the root or the root index? 2. So it should be to the 2nd power? Yes, yes? Yes. No! Not the 2nd power, the 1/2 power. 1/2. I trick people all the time. That's what people want to say, the square root of a number is the same as squaring the number. No, it's not. Right? There's no way you're going to take a square root of 5x and say it's the same as 5x squared. That's you not thinking it all the way through. It's a 1/2. Did you have the C? Like a 5x square root is not the same as 5x squared. I get that all the time too. When the temperature differential hits you, yeah, and you have a little seizure. Speaking of little seizure, I haven't had one in a while. I get to drive on April 4th. Yay! And I might just drive to Little Caesars and get some pizza. That's my new nickname at home, by the way, Little Caesar. I'm like, thanks, family. Y'all must love me. Now look, we can simplify, can't we? I have a power raised to a power. Ah, what do I do with those two? I multiply, and I get 1/2 times 3, which is what? 3/2. Yeah. Well, let's talk about that. Is that equal to 5x to the 3/2 power? No, it's not. Okay, because the one on the left is 5 to the 1st times x to the 3/2. Wait, but also, like, yep. What is that? The beginning problem, if they didn't have parentheses, then would you have to have them? Because they're both under the radical, they're both to the 1/2 power. And if you don't put parentheses around the 5x, we have to do PEMDAS. We have to do order of operations, which means the exponent is only attached to the x, and then we'd multiply by 5. So they're not the same. You would need parentheses around the 5x. Now, here's another advantage to having the exponent as a fraction. I can use the rule of exponents. Remember this? If you have a times b to the 2nd power, that's the same as a squared b squared. You remember that? It's like having a 1 on both of them and multiplying the exponent times both of them. If I had a squared b cubed, whoa, to the 2nd power, that would be the same as what? A to the 4th, b to the 6th. Yeah, I essentially multiply, I distribute to the exponents. Well, guess what I can do right here? This is 5 to the 1st, x to the 1st. So this is 5 to the 3/2, x to the 3/2. And that's what it's equal to. So you need the parentheses there unless you're going to distribute that exponent to both of them. Okay. People hate the rules of exponents. I used to spend almost a full month in pre-cal after summer just going over rules of exponents because people were so bad at them. We were told we're not allowed to do that this year, so we've been reviewing in warm-ups. But it's super important, okay? Super important. Let's review those rules of exponents since they've been coming up. Exponent rules. Exponent rules. First of all, we have x to the a times x to the b. When you're multiplying and the bases are the same, what do we do with the exponents? We add them. That's a plus b. Yes, yes? Okay. Now let's do division. If you have x to the a divided by x to the b, what do you do with the exponents? You subtract them. X to the a minus b. Yes. If you have x to the a raised to the bth power, that becomes what? X to the ab, a times b. Yeah. And now we can add this. The nth root of x to the m is what? X to the m over nth power. Yeah. Yeah. So there's your new exponent rules. We've added one to it. Okay. Write in radical form and then simplify. Okay. Negative 27 to the 5/3. Remember I said if it said to evaluate it and it's in fractional exponent form, you probably don't think in terms of fractional exponents. So it's helpful to convert it back to radical form. Okay, that's the language that we know. So let's do that. The base is negative 27. Is it the fifth root of that or the cube root of that? The root is 3, so it's the cube root. Yes, yes? Okay, good. Now, here's my question to you. Where do I want to put the 5 if I'm doing it without a calculator? Do I want to put the 5 underneath the radical or outside the radical? Outside, yes. Because if I put it on the inside, now I have to know what negative 27 to the 5th power is. No, thank you. Negative 27 times itself? No. 5 times? No. But if I put it on the outside, I can take the cube root first. That makes more sense. Okay, let's try that. Something to the 5th power. Let's evaluate the inside. What is the cube root of negative 27? That is, what number times itself 3 times is negative 27? Not 3, but negative 3. Remember, the cube root of a negative number is going to be a negative number because you have an odd number of them. Negative times negative is positive. Positive times negative is negative. Okay? The cube root of a negative number is a negative. Hey, believe it or not, the 5th root of a negative number is also a negative number, and the 11th root of a negative number is a negative number. If it's an odd root index and it's negative under the radical, you're going to have a negative answer. All right, now I've made the problem a lot more manageable. What's negative 3 to the 5th? First things first, is it going to be positive or negative? It's going to be negative because I have an odd power. Now I can at least go off to the side and say 3 times 3 is 9. There's 2 of them. And then 9 times 3, there's another one, that's 27. I could at least do this, 27. There's my third one. 27 times 3. There's the fourth one. That's going to be 81. And then 81 times 3. There's the fifth one, is 243. I just did the multiplication. Now, even if you had your calculator, you could do 3 times 3 times 3 times 3 times 3, 5 times to get 243. I have it here. I was just focusing on the 3's because I know a negative to the 5th power is going to be negative. And now I just focus on the 3's. If this were a 6 instead of a 5, then you would have a positive answer. Yeah, if it's raised to an odd power, it's going to, and it's negative, it's going to be negative. If it's an even power, it's going to be positive. Yeah, there we go. We need to be able to do this without a calculator. Now, if you had your calculator, you could easily just type this expression in and get the answer and verify it. In fact, there were a lot of people that were asking me on the test where the cube root button is because they wanted to type in the equation. Let's say I have the cube root of the quantity 2x minus 3, and you don't know where the cube root button is. But you know where the caret button is, right? You know how to raise something to the 3rd power. How can we rewrite that function so that we don't have to worry about where the cube root button is? It's the same as all that to the what power? Boom. There you go. Caret 1 divided by 3. You got it. It's the same thing. You don't need to know where the cube root button is anymore because you just raise it to the 1/3 power. Presto magic. All right, look at this one. 125 eighths to the 2/3 power. Whoa. Which one should we do first? Should we try to square it first, make it bigger? Or should we try to cube root it first? Cube root it, right? Because the 3's in the denominator. Let's write it like that. Let's take the cube root of 125 all over 8, and then we'll square the result. Let's go small before we go big. Okay, now, here's another property right here. Another property that we could talk about. Or how about the cube root of A over B is the same thing as the cube root of A over the cube root of B. Okay, it's like giving both the numerator and the denominator the 1/3 exponent. Okay, so instead of trying to figure out what the cube root of a fraction is, maybe that's just the cube root of 125 all over the cube root of 8. And we can square that result. What we're doing is we're doing divide and conquer. We're making things easy on ourselves by looking at components here. Now, if I expect you to do this without a calculator, these numbers are going to be nice numbers. What would the cube root of 125 be? What number times itself 3 times? It's 5. Because 5 times 5 is 25, and 5/4 is $1.25. So the cube root of 125 is 5. What's the cube root of 8? We already said 2. So really it's 5/2 squared. Now 5/2 squared is really 5 squared 2 squared, using the property in reverse. 5 squared 2 squared is 25 over 4, okay? What we're trying to do is to get you to be proficient with just writing the expressions in a different form. By way of the rational exponent, you can simplify things. By way of the radical, you can evaluate things. So 125 eighths to the 2/3 power is just another name for 25 fourths. Fun, 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 fun. You know how you get good at doing these kind of things? Practice, and then guess what the second one is? Practice, and guess what the third one is? Practice. That's right. Because I guarantee, pre-cal kids are still weak in this. Calculus kids are still weak in this. Y'all are Algebra 2 kids. Right now, you can nick this in the bud. You can get good at it right now and not have to be stumbling later on. Okay? Write using rational exponents and then simplify. Okay. The square root of -4th to the 6th. There's two options here. Do you want to raise -4th to the 6th power? No, but we do know it's going to be what? Positive or negative? It should be positive because it's to a 6th power, which is an even number. So -4 to the 6th is going to be the same as 4 to the 6th. But I still don't want to do 4 to the 6th, do I? That's 4 times 4 times 4 times 4. That's like 16 squared. But I could do this. Watch. I could say that it is -4th to the 6th power, and then all of that raised to the what power? Because it's under a radical square root. A 1/2 power. Yes, yes. Got it? That's getting rid of the square root, writing it as a half. And now look, I can use the rules of exponents. When I raise a power to a power, what do? I multiply. What's 6 times a half? 6 over 2, which simplifies to what?
3.
3.
So would it make it negative now?
Now it's negative now. Or is it? Ah, we are at a fork in the road. And this is a very, very important distinction. The order of operations matters for the final answer, but not for the evaluation. In the original problem, we're actually raising it to the 6th power what? First or second? First. And that's going to make this negative number what? Positive. Positive. And then the square root of a positive number is going to be what? Positive. By doing this first, I've made it an odd number, which now is going to give us a negative answer. Should the answer be positive or negative based on what we started with? Based on what we started with? No. It should be a positive number. Okay? A negative number to the 6th power is going to be a positive number. So really this should be what? Not -64, but what? Positive 64. Oh, no. 4 cubed, 4 times 4 times 4. So this is getting into a more subtle distinction when we talk about the domain. The order doesn't matter to get to the magnitude, the size of the number, but the original order of operations dictates whether your final answer is positive or negative. Okay? Very, very important. Lots of little things here. That's why practicing is so important. All right, the last one, do on your own. Simplify it as much as you can on your own. See what you can do. Scooby-Dooby-Dooby-Dooby and Scrappy-Doo-Doo. Shaggy and Fred and Velma. What makes these problems so wonderfully delicious is that you can actually do them in any order. You can go small then big or big then small. You can treat them as radicals or you can treat them like fractional exponents. Either one. Or you can even do a combination of both. Looking at it, here's what I see most of y'all doing. That to the fifth power is the whole thing. So here's what some of y'all did. We'll go down this fork first. You wrote 8x over y cubed. Since it's all under a cube root, that becomes to the what power? To the 1/3 power. And then all of that is still to the what power? Fifth power. That becomes 8x over y cubed to the what power?
Have your attention for just a moment. Teachers and students, we will be remaining in our third period class for advisory today. The only students that should be transitioning for advisory today are those that have been assigned a targeted advisory group. So once again, all other students need to be remaining in advisory. Teachers, if you can please help us out, this Wednesday we will be having all junior students take the SAT. During advisory today, we need you to look at the email from Ms. Morris and go through. Students, you need to be taking a picture of your test ticket on your.
You know, we'll go over this tomorrow. It's the last one. We'll use it kind of like a warm up, okay?
Where you will be
Feel free to finish it if you think you know what you're doing.